But you're not supposed to be in the video. Exactly.
For almost 2,000 years, humanity looked up at the night sky and saw a universe that revolved around us. The sun rose in the east, it set in the west. The stars wheeled overhead in perfect circles, and at the center of it all, stable, unmoving, and special, was Earth. It wasn't arrogance, it was just simply observation, it was logic, it was by any measure available obviously true. And it was completely wrong. This is the story of how we discovered that the universe didn't care what we believed. A model that worked for 14 centuries, predicting eclipses and guiding ships, collapsed because of something almost invisible. A tiny difference in the sky, no bigger than a quarter of your thumbnail. That's how small the error was that brought down an entire worldview. In the 2nd century, a mathematician named Claudius Ptolemy sat down in Alexandria and attempted something audacious. He wanted to build a machine, but not of bronze or wood, but of mathematics, that could predict where any celestial body would be at any night, past or future. And he succeeded. His system placed Earth at the center. The moon orbited closest, then Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and finally the fixed stars on crystalline spheres. Each body moved in perfect circles. But there was a problem. The planets didn't behave. Mars in particular had this very annoying habit of slowing down, stopping, and then moving backward across the sky before resuming its normal path. We call this retrograde motion. How do you explain backward motion in a system built on perfect forward circles? Ptolemy's answer was elegant. Circles on circles. A planet didn't just orbit Earth on a large circle called a different. It also moved on a smaller circle called epicycle, whose center rode along the different. Layer enough circles together, adjust their speed and sizes, and you could reproduce the wandering dance of Mars. And of course, besides that, he added another trick: the equant. This was an imaginary point, offset from Earth, from which planetary motion appeared uniform even when it wasn't. It was a mathematical cheat, but it worked. And here's the remarkable thing. Ptolemy's model could predict the position of the Sun to within 1/16th of a degree. I mean, that's accurate enough to plan harvests, navigate oceans, and calculate the date of Easter for centuries. That is more than just good enough. And for 100 years, this system wasn't just accepted, it was indeed very, very useful. It was the foundation for navigation, agriculture, religion, and even astrology. To question it wasn't just philosophically dangerous, it was practically absurd. Why would you abandon a machine that worked? It makes no sense, doesn't it? Nicolaus Copernicus was not a rebel. He was a church administrator, a physician, a man of deep faith who spent most of his career managing estates and treating the sick. But he had a hobby that consumed his private hours. He was trying to fix Ptolemy's machine. Not to replace it, but to fix it. This equant really bothered him. It felt like a violation. Motion that only appeared uniform from an arbitrary point? That was not the elegant cosmos Aristotle had described. That was a complicated workaround. So Copernicus asked a simple question. What if we moved the center? What if the Sun, not the Earth, was at the center. What if Earth was just another planet spinning on its axis once a day and orbiting the sun once a year? It was, after all, an old idea. Aristarchus of Samos had proposed it 18 centuries earlier, but Copernicus developed it mathematically, working out the implication over 3 decades. And here's where the story gets complicated. Because Copernicus' system was not simpler, it still required epicycles, just smaller ones. It still couldn't predict planetary positions much better than Ptolemy's, and it raised enormous physical problems. If Earth is moving at tremendous speed around the sun, why don't we feel it? Copernicus had no good answers. He published his full work on the revolution of the celestial spheres in 1543, the year of his death. According to legend, he received the first printed copy on his deathbed. The preface, added without his permission, called the heliocentric idea a mere calculating device, not a description of physical reality. Perhaps that heading saved the book from immediate controversy. For decades, it was read mainly by specialists, appreciated for its mathematics, but dismissed for its physics. However, the seed was planted. In November 1572, a star appeared where no star had been before. It blazed brighter than Venus, visible even in daylight, then slowly faded over 18 months. Today, we know that as a supernova, the explosive death of a massive star. But to 16th century Europeans, it was impossible. Aristotle had taught that the heavens were perfect, eternal, and unchanging. New stars didn't just happen. A 25-year-old Danish nobleman named Tycho Brahe measured that star obsessively. He calculated its parallax, the apparent shift in position when observed from different locations, and found none. The star was far beyond the moon in the supposedly immutable realm of the celestial. 5 years later, Brahe tracked a comet and proved it moved through the space where the crystalline spheres should have been. The spheres, those solid, nested orbs carrying the planets, couldn't exist. If they would exist, they would have shattered. The King of Denmark gave Brahe an island and unlimited funding to build the finest observatory in history. For 20 years, Brahe measured the positions of stars and planets very carefully, down to about 1 arc minute, which is as precise as you can get without a telescope. But Brahe was no Copernican. He couldn't accept a moving Earth. If Earth orbited the Sun, nearby stars should shift positions over 6 months. Stellar parallax. Brahe looked for it very closely and found nothing. We know now that the stars were simply too distant for his measurements. But Brahe was an empiricist. He wouldn't accept something that he could not measure. So he compromised. In Brahe's system, the planets orbited the Sun, but the Sun, carrying all the planets, orbited a stationary Earth. I mean, mathematically it was equivalent to Copernicus. Philosophically, on the other hand, it kept Earth at rest. Brahe never published his planetary theory in full, but his data, 20 years of the most precise observation ever made, would outlive him. And that data would change everything. Johannes Kepler was a mystic. He believed the universe was designed by God according to mathematical harmonies, that the spacing of planetary orbits followed sacred geometric ratios. His first book argued that the orbits of the 6 known planets corresponded to the 5 Platonic solids: the tetrahedron, the cube, octahedron, dodecahedron, and icosahedron, nested inside each other. It was nonetheless beautiful, and it was wrong. And Kepler spent his life proving it wrong with his own work. In 1600, Kepler joined Brahe in Prague. The collaboration lasted only 18 months before Brahe died. But Kepler inherited the treasure: decades of meticulous observations, especially of Mars. Kepler became obsessed with Mars. Its orbit was the most eccentric of the known planets, the hardest to fit the circular motion. For years, he tried to make Brahe's data match a circular orbit. He tried different combinations of circles, epicircles, equants, and nothing worked. The best he could do left an error of 8 arc minutes. 8 arc minutes. 1/4 of the apparent width of the moon, which is even hard to see with the naked eye. Kepler wrote, and I quote, "These 8 minutes alone will lead to the reformation of all astronomy." End quotation. He refused to ignore them. And then, after years of failure, he tried something that must have felt like heresy. What if the orbit wasn't a circle at all? A flattened circle with 2 focal points. If the Sun sat at one focus, not at the center, and Mars swept out equal areas and equal times, it fit perfectly. Every observation Brahe had made, every position of Mars across 2 decades, it all fell in a place. Kepler had discovered 2 of his 3 laws of planetary motion. Planets orbit the Sun in ellipses, and they sweep out equal areas in equal times. The 3rd law, relating orbital periods to distances, would come a decade later. And here is the heartbreak. Kepler had spent his life believing the universe was built on perfect geometry, sacred shapes and divine circles. His own discovery, however, destroyed that dream. Ellipses are not divine. They're just what happens when gravity pulls things together. And Kepler had never really fully accepted it. He spent his remaining years trying to reconcile ellipses with his mystical vision. He never could, however, but the universe didn't care what Kepler believed, it cared what math said. And math said ellipses. In the summer of 1609, Galileo Galilei heard rumors of a Dutch invention, a tube with lenses that made distant objects appear close. Within months, he had built his own version, and then a better one. He pointed it at the sky. What he saw was impossible. The moon wasn't a perfect sphere. It was covered with mountains and craters, rough as Earth. Jupiter had 4 moons of its own, orbiting in plain violation of the principle that everything must orbit Earth. Venus showed phases like our moon, proving it orbited the Sun. Galileo published his observation in the Starry Messenger in 1610. It made him famous across Europe. It also made him dangerous. The Catholic Church had adopted Aristotle's geocentric universe as compatible with Scripture. Psalm 93, and I quote, "The world is established. It cannot be moved." End quotation. Joshua commanded the sun to stand still, not the earth. To challenge geocentrism was to challenge biblical interpretation. In 1616, the Inquisition declared heliocentrism formally heretical. Galileo was warned to abandon and not defend his idea. For 16 years, he complied. Then in 1632, he published Dialogue Concerning the Two Chief World Systems. It was framed as a balanced debate between a Copernican and an Aristotelian. But the Aristotelian character was named Simplicio, the simpleton, And into his mouth Galileo placed the Pope's own theological arguments. Pope Urban VIII has been Galileo's friend and patron. The mockery was unmistakable. In 1633, Galileo stood trial before the Inquisition. He was found vehemently suspected of heresy and sentenced to house arrest for the remaining 9 years of his life. His book was banned, and heliocentrism was forbidden. But here's what matters. The trial wasn't about evidence. Galileo's observations of Jupiter's moons and Venus's phases were consistent with the tectonic system, where planets orbit the Sun, but the Sun orbits the Earth. They didn't really prove that Earth moved. The definitive proof, stellar parallax, wouldn't come for another 2 centuries. The triumph of heliocentrism needed something more than observation. It needed explanation. On 5th of July, 1687, Isaac Newton published a book with the quite intimidating title, The Mathematical Principles of Natural Philosophy. It contained the laws of motion and universal gravitation, and it ended the debate forever. Newton showed that the same force pulling an apple to the ground also held the moon in orbit around Earth and the planets in orbit around the Sun. There was no separate physics for heaven and earth. The celestial and terrestrial were united under a single law. Elliptical orbits weren't arbitrary. They were the necessary consequence of gravitational attraction between masses. The shapes of orbits, the speeds of planets, the relationship between period and distance, all of it followed from a single equation. And here was the killing blow to geocentrism. Newton's mechanics explained why we don't feel Earth's motion. Everything on Earth moves with it. Throw a ball straight up, and it continues moving with the Earth's rotation, even as it rises and even as it falls. The physics of a moving Earth and a stationary Earth aren't distinguishable from the surface. But gravitationally, a stationary Sun with planets orbiting, it is the only configuration that makes sense. The Sun contains 99.86% of the solar system's mass. In Newton's universe, the lighter objects orbit the heavier. Earth orbits the Sun. For the same reason, an apple falls towards Earth. Mass attracts mass, and the Sun's gravity dominates. After Newton, no serious astronomer defended geocentrism. Not because the Church changed its mind. The Vatican didn't formally accept heliocentrism until 1822, but because Newton's framework was so powerful, so predictive, and so useful that it became the foundation of all physics for all the next 2 centuries. There is a lesson in the story that goes beyond astronomy. For 14 centuries, the geocentric model wasn't wrong in the way we usually mean wrong. It did make accurate predictions. It was supported by the greatest philosophers. It fit human intuition and daily experience. The Sun does appear to rise and set. The Earth does feel motionless. The model failed not because it was, stupid or lazy or poorly constructed, but because it was built to preserve assumptions about perfect circles, about special positions, about the distinction between heaven and earth, rather than just to follow evidence wherever that led. We now know that the Sun isn't the center either. It's one star among hundreds of billions in a galaxy that's itself one of trillions. The observable universe has no center, or every point is equally the center, depending how you measure. And Earth is a mote of dust suspended in a sunbeam, as Carl Sagan once said. A small world in an endless cosmos. But here's the thing, the smallness does not diminish us. We're the ones who figure it out after all. We are the descendants of those who looked up at wandering lights and said, I want to understand. That drive to measure, to question, to refuse to ignore 8 arc minutes, that's what makes us remarkable. Not our position in space, but our position in the story of understanding. Our curiosity. If this exploration of how we discovered our place in the cosmos resonated with you, if you want more stories about the curiosity that changed science and the people who reshaped how we understand the universe, please consider to subscribe to this channel and share with someone who still looks up and asks questions. Thank you for watching and see you in the next one.